All right, now that we're familiar with logarithms, let's look at this pH thing. Notice, by the way, that pH is spelled with a lowercase p and a capital H. It's a way of expressing the concentration of the hydrogen ion, or formally we might say something like the H3O, the hydronium ion with the brackets around it, in an easier way, and what we do is we make use of the logarithm to make this easier. So here's the definition of pH. It is a mathematical definition. It is defined as the negative, and don't forget that negative, logarithm of the hydrogen ion concentration, or if you like, the negative logarithm of the hydronium ion concentration. Now, you may ask, why do we need the negative? Well, that makes the pH come out positive, as we'll see here when we do some examples. And since the pH is defined by logarithms, that means that each pH value differs by 10 times the hydronium ion concentration. So I have this little question here. What's the difference between a pH of 6 and a pH of 5? Why don't you pause for a moment and think about that. All right, so hopefully you wrote something down here. The difference between a pH of 6 and a pH of 5 is 10 times the concentration of hydronium ion. And interestingly, because it's got this negative sign out here in front, negative 5, is larger than 6, because negative 5 is a bigger number than negative 6. And so this pH of 5 has a 10 times bigger hydronium concentration than pH of 6. All right, now, a similar quantity, but one that's less well known outside of chemistry, is the POH. And you could probably guess that the POH is defined as, again, the negative log of the hydroxide ion concentration. So just like the pH is the negative log of the hydrogen concentration, the POH is the negative log of the hydroxide ion concentration. I've heard this, that P stands for power of the hydroxide, so the logarithm is the exponent, so it gives you the exponent of the hydroxide is what it does. Okay, now we're going to go through a relatively lengthy derivation, which you'll like where it ends up. If we start back here at the ionization constant, or ionization product constant for water, then the hydronium concentration of hydroxide is this value, 1 by 10 to the negative 14th. But I'm going to do something here mathematically. I'm going to take the logarithm of everything. So it's the logarithm of Kw. It's the logarithm of this stuff, so I just put parentheses around that to lump it together. And then it's the logarithm of the stuff on the end, so log of 1 by 10 to the negative 14th. And I'm going to drop some of that out now here. So I then dropped out the log of Kw because it's not going to give me anything that I really care about. And I'm going to multiply through by negative 1. So if I put a negative in front of that and a negative in front of this. All right, then I'm going to do another simplification here. You may know that if you multiply numbers together, you add together their logarithms. Since these numbers are multiplied together, I can add the logarithms of each. And I multiply the negative in on both of them. So I have the negative log of H3O plus the negative log of OH, and the log of this is just 14, but the negative sign makes it positive. Now look at this. What is this? And what's this? Well, this is pH, and this is POH, and here's what we end up with. When we add together the pH and the POH, they must always add up to 14. Next, we will be looking at some examples of how to do pH problems.